So directly we'll start with transmission line. Now what is transmission line? Transmission line is an electrical device or electrical entity or electrical system, you can say, through which we pass a signal from one point to another point. So it guides the signal from one point to another point. So if there are two different points, one point is A, another point is B. For example, at one point you are there, at another point your friend is there. So between you and your friend, if you want to communicate, send some information from you are trying to send information to your friend who is at another end, then we use a transmission line unless you are using a phone. Phone is a wireless device. Telephone is sorry, these mobile phones are wireless device. But if you are using wired device, then you are using transmission line. There are various types of transmission lines. Our concentration in this class, today's class, will be on two-wire parallel parallel wire transmission line. That will be our concentration. And we need the theory of this transmission line. We'll develop the theory of transmission line. Let us consider a transmission line section. The length of the section of transmission line is L. So whenever this length on the section of the transmission line is significant compared to wavelength, then we need the transmission line theory. We have to understand what is the theory behind working of the transmission line. What is the principle behind the working of transmission line? That is what we want to understand. So for that, when that will be required? When the length of the transmission line is significantly small compared to the wavelength, or it is significant compared to a wavelength. So it can be expressed in terms of wavelength. For example, let us see these two cases, the top case and the bottom case. In the top case, the wavelength is much higher than the transmission line. Transmission line is the red one is the transmission line section. Yellow is the a signal which is a sinusoidal signal or a sine wave, sine signal that you know. It is a sinusoidal signal. Now you can see in the top, the length of the transmission line is very small compared to the wavelength of the signal. Now there also you can see that over the transmission line, the signal value almost remains constant. It does not change. So a transmission line theory, we are not required to apply it here. You can always apply the transmission line theory, but here we do not require the transmission line theory to be applied, because the voltage over the transmission line section or the current over the transmission line section is constant. It is not changing. Look at the top figure. That is what we are discussing. So since it is not changing, so we are not required to apply the transmission line theory. But if you look at the bottom figure, at every point of the transmission line, that is the two red lines, that is the transmission line section, at every point of the transmission line section, there will be a different voltage or different current, because the wavelength is so small that the transmission line length is comparable to the wavelength. You can express the transmission line length in terms of the wavelength. Therefore, you can say, or we always apply, when the wavelength is small or frequency is high, we always apply the transmission line theory to understand the transmission line. So that is one point. Then the second point is it is changing the voltage and the current value are changing over the transmission line. From circuit theory that you have read, electrical circuits you must have read in your undergraduate courses or pre-college courses. The circuit you must have read, Ohm's law, Kirchhoff's law, etc. You are expected to be acquainted with those things. Since you know those things, you know that if we have a resistor, then across the resistor there is a voltage drop. So at one end of the resistor, if voltage is V1, at other end of the resistor, the voltage will be V2, because across the resistor there will be a voltage drop of V2 minus V1. That drop, so that is why the voltage will change. Voltage changes because the presence of a resistor. Here we will say it impedance. Instead of calling it a resistor, we will call it an impedance. An impedance. What is an impedance? You know what is an impedance? Impedance is combination of resistor and or a uh, resistive device and a reactive device. A resistive device is basically a resistor or a resistance or a conductance. Reactive devices are capacitance and inductances. So a combination R plus Jx is impedance. So R is resistance, X is reactance. So X can be equal to omega C, or X can be equal to omega L or 1 upon omega C. If it is inductance, it will be omega L. If it is capacitance, it will be 1 upon omega C. So that is what is an impedance. Now across an impedance there will be voltage drop. So you can say that when we are looking at this transmission line section, at every point there is a voltage drop or a voltage change. Since there is a voltage change at every point, you can say that the transmission line consists of many impedances or many admittances which are continuously distributed over the transmission line. That is what we can say. So, transmission line itself is a distribution of both impedances and admittances. Give me a minute. ଟିକେ ଇଏ କରିଦିଅ କିଏ ଗୋଟେ ଜଏନ୍ କରୁଛି ପିଲା ଜଏନ୍ କରୁଛି କରେଇ ଦିଅ ଏଟା ବନ୍ଦ କରିଦିଅ ଏସ୍କେପ୍ ସେଟାକୁ ଯା ଆରଟାକୁ ଯା କ୍ରୋମ୍ କୁ ଯାଅ କ୍ଲିକ୍ କର ତାପରେ ଆଡମିଟ୍ କର ତାପରେ କ୍ଲିକ୍ କଲେ ତ ହବ ନା ରଖିଲେ କେମିତି ହବ ହଁ ସେଟା କିଛି କାମ ନାହିଁ ଏବେ ଆସୁଛି କି ନାହିଁ ଦେଖିଲ ଏଟା ତ ହଁ ଇଏ କୁ ଯା ପ୍ରେଜେଣ୍ଟେସନ କୁ ଯା ପ୍ରେଜେଣ୍ଟେସନ ମୋଡ କୁ ଯା ତଳେ ତଳକୁ ଯା ତଳକୁ ହେଲେ ଏଠିକି ଡାକ ତମେ ପାରିବନି So as I told you, the transmission line has two wires. So two wires means two conductors. It has two conductors. So it is a two conductor device. There can be different forms of having a transmission line. We are we are concerned with two parallel wire transmission line, which is on the top right hand side. If you look at the top right hand side, there are two parallel wires. On the top left hand side also there are two wires. One is a central conductor. Surrounding that conductor there is another conductor. So it is like a cylinder, hollow cylinder. Within the hollow cylinder there is one conductor, a solid cylinder. So there are two conductors. So hollow cylindrical conductor and a solid cylindrical conductor. And the solid cylindrical conductor is along the axis of the hollow cylindrical conductor, that is called a coaxial transmission line. That we will discuss later in the maybe in the next class or on the class following that. But transmission line is a two conductor device, that we understood. That you should know. Then the other thing is that we are discussing is the transmission line can be viewed as a distribution of uh, electrical components like resistance, conductance, capacitance, and inductance. Now there are four per unit length parameters in the transmission line. So we can say that C, capital C, is equal to capacitance per unit length. Its unit will be farad per meter. Capital L is inductance per unit length. Its unit is Henry per meter. R is resistance per unit length and its unit is ohms per meter. G is conductance per unit length. Its unit is Siemens per meter. These are per unit length. When we say per unit length, that is per unit length of the transmission line. So per unit length, first we define what will be the resistance, inductance, conductance, capacitance in the transmission line. So this is how we define. These are the values per unit length on the transmission line. Then we can and start the analysis of the transmission line. Now we are considering a small section of the transmission line, minuscule section of the transmission line, which is very small. So length of the transmission line is delta Z. Look at the top figure. Length of the transmission line is delta Z. Along the transmission line, there will be voltage at every point. So V, you can see between the two wires, we have written VZT. That means B is varying, B is voltage that is varying with time. It is a time varying voltage because we are considering a sinusoidal signal or any other signal which is not DC, AC. Since we are considering AC, so it is time varying. Therefore, V is a function of time as well as V is a function of Z. Z is the distance or the position. So V or voltage is a function of position and time on the transmission line. This section of the transmission line is very small, delta Z. Therefore, the signal wavelength is comparable to the transmission line length. Okay. Similarly, the current is written above the transmission line IZT. Current is also varying along the distance or on the transmission line at every point. The current is different. That is why it is a function of Z, and it is varying with time. That is why it is a function of T. So I is a function of Z and T. V is also a function of Z and T. Now, on this transmission line of section delta Z, what will the resistance? Resistance will be, because R, we have defined R is the resistance per unit length. Length of the transmission line is delta Z. Therefore, resistance will be R delta Z. Similarly, inductance of the transmission line will be L delta Z. Capacitance will be, since these are two wires, so between the two wires there will be capacitance. As you know, between two plates there is a capacitance. So similarly, here plates are squeezed so that it becomes a wire. So between them there will be capacitance. So capacitance will be C delta Z. Similarly, G delta Z is conductance. So capacitance and conductance are in parallel. Resistance and inductance are in series on the transmission line. Now at the left end current enters, it is IZT. At the right end current leaves the section delta Z. So at the right end, if the left end is Z, right end will be section of length of the transmission line is Z delta Z. So right end will be Z plus delta Z. So it is a function, it will be IZ plus delta Z T. Left hand is IZT, right hand is IZ plus delta ZT. So entering current is IZT, current leaving this section is IZ plus delta ZT. Similarly, voltage entering is at the entering point, entry point voltage is VZT. At the leaving point where the voltage or the energy leaves the section delta Z, there the position is Z plus delta Z. Therefore, voltage there will be Vz plus delta Zt. Okay. Now we will use the Kirchhoff's law for analyzing the transmission line. So once you know that, you can always use the Kirchhoff's law. So now find out what is Vzt, voltage at the left end or the entering end. Now instead of entering end, I will call left end and right end. So at the left end, voltage is Vzt. Now what will be the at that Vzt? Vzt will be the voltage across the resistor plus the voltage across the um, inductor plus the voltage across the capacitor or conductor. Now on the voltage across the uh, capacitor or conductor is given Vz plus delta Zt, that we know, that is at the right end. The voltage at the right end is the voltage across the capacitor or conductor. So that we can start with that. So Vzt is equal to voltage across the conductance or capacitance, that is Vz plus delta Zt, plus the voltage drop across the resistor. Resistance is R delta Z. Current passing through that R delta Z is I ZT. Therefore, the voltage drop is IZT into R delta Z. As you know, V is equal to IR. Use that. So IZT into R delta Z. Similarly, across the inductors, as you know, V is equal to L dou I by dou T. So use that. L is L plus delta Z here. Inductance value is L plus delta Z. So that will be, last term will be plus L delta Z dou I Z by ZT by dou T. Similarly, let us find out what is the current. Current is IZT, that is at the left end. What will be at the right end? The current passing through the resistance or the inductance, that much current, that is the current. Then the current that goes through the conductance and the current that goes through the capacitance. So that you have to add. So the current that goes through that is passing through the R delta Z, L delta Z, that is the current which is coming out. So current coming out is IZ plus delta ZT. So IZT is equal to IZ plus delta ZT plus the current through the conductance. Current through the conductance is voltage across the conductance into the conductance. So Vz plus delta Zt into G delta Z. Then current across the capacitance is the time derivative of the voltage across the capacitance, which is dou V by dou T, dou V Z plus delta Z T by dou T into the capacitance value, that is C delta Z. So IZT will be the bottom line. So these are the two expressions for voltage and current. So we have found out the two expressions for voltage and current. Once we have done that, then what we will do is we will take all voltage from the first equation, take all voltage term to the left hand side. From the second equation, we take all current term to the left hand side. Then we divide both the sides by delta Z. So that gives us V Z plus delta ZT minus V ZT by delta Z is equal to minus R I ZT minus L dou I by dou T. Similarly, IZ plus delta ZT minus IZ by delta Z is equal to minus G VZ plus delta ZT minus C dou VZ Z plus delta ZT by dou T. So this much we know. Now let us assume that delta Z approaches 0, an infinitesimally small length of the line. So delta Z approaches 0. When delta Z approaches 0, Vz plus delta Zt minus Vzt by delta Z will be dou V by dou Z. So write that dou V by dou Z. This you know from calculus. How do you define derivative? Dy by dx. If the derivative is dy by dx, you define that as limit delta x goes to 0 and delta y by delta x, where delta y is equal to y plus delta y minus delta minus y. So from that formula you use here. So that gives you dou v by dou z is equal to minus ri minus l dou I by dou t. Similarly, dou I by dou z is equal to minus gv minus c dou v by dou t. These two equations are called telegrapher's equation. In your examination, many of the time people ask you, question will be derive the telegrapher equation or discuss about telegrapher equation. The telegrapher equations are the basic equations for under the transmission line theory. Based on the telegrapher equation, the transmission line theory is developed. We have to solve the telegrapher equation. Now you can see that this telegrapher equation is a partial differential equation, and these are two equations which are coupled to each other, which means in the first equation you have dou v by dou z, in the second equation you have dou v by dou t. Little graph. In the second equation you have dou v by dou t. Similarly, in the first equation you have dou I by dou t. In the second equation you have dou I by dou z. So both the equation have v and z, v and t, and both the equation have variables z and t. So these two equations are coupled equations. So telegrapher equations are a set of two equations which are coupled to each other and which are partial derivatives, which contains partial derivatives. So these are differential equations which are coupled to each other. Now let us combine these equations. What we'll do is take the derivative of the first equation with respect to z. So that makes it dou square v by dou z square is equal to minus r dou I by dou z minus L dou by dou z and dou I by dou t. What I am doing is just taking the derivative with respect to z. Now on that we can do one thing, dou by dou z, dou I by dou t. There we can interchange the derivatives, dou by dou t by dou y dou z, that we can do. Dou by dou z into dou by dou z of dou I by dou t is same as dou by dou t of dou I by dou z. So write it that way. So switch the order of derivative. So that becomes the right hand side now becomes minus r dou I by dou z minus L dou by dou t of dou I by dou z. Now we know the expression for dou I by dou z, which was the second equation, second telegrapher's equation. So we'll put that value. So if you put that value, dou I by dou z value put the value of dou I by dou z. Dou I by dou z is minus gv minus c dou v by dou t. If I put that, so that will become, now the right hand side becomes minus r into minus gv minus c dou v by dou t minus L whole into minus g dou v by dou t minus c dou square v by dou t square. Now you can see that this equation we can write as once uh, we use this equation, we can rewrite it uh, easily. We can rewrite is easily dou square v by dou z square is equal to minus r into minus gv minus c dou v by dou t minus l minus g minus l into minus g dou v by dou t minus c dou square v by dou t square. Now you can take dou v by dou t common, that will give you rc plus lg into dou v by dou t plus gv have into r plus uh, lc into dou square v by dou t square. So dou square v by dou t square minus rg into v minus rc plus lg dou v by dou t minus lc dou square v by dou t square is equal to 0. We have taken everything to the left hand side. So if you take everything to the left hand side, you get this equation. This same differential equation holds for I, which means just replace V with I in this equation. So there will be, this equation will hold for I. And remember that this equation has no exact solution. So there will be inexact solution, otherwise we have to do some assumptions. Under assumptions we can find out some solutions for this. So one assumption is the wave is time harmonic in nature, or the signal is time harmonic in nature. If the signal is time harmonic in nature, then its time variation will be of the form exponential j omega t, or e to the power j omega t exponential j omega t. If its form is exponential j omega t, if you take its derivative with respect to time, dou by dou t is equivalent to j omega. So for dou by dou t, put j omega in the above equation. That will give you now dou square v by dou z square minus rgv minus rc plus lg dou v by dou t minus lc dou square v by dou t square. Now dou v by dou t will be j omega v, dou square v by dou t square will be j omega into j omega into v. J omega into j omega is minus omega square, because j is minus 1. So from that you will get d square v by dz square. Now look at these two equations. The first equation is partial derivative. The second equation is a complete derivative. Why? In the first equation we have derivatives with respect to z and t. Now with the derivative with respect to t is removed, because dou by dou t is j omega, that is what we are using. Since with respect to t is removed, only there is derivative with respect to z. So therefore it becomes a complete derivative. So dou square v by dou z square minus rgv minus rc plus lg into j omega v minus lc into minus omega square v is equal to 0. Okay. And so from that you will get d square v by dz square is equal to rgv plus j omega rc plus lg into v minus omega square lc into v. So both the sides are equations in terms of v. Now, and note here one thing, Rg plus j omega into whole into Rc plus Lg minus omega square Lc, that you can write as R plus j omega L whole into G plus j omega C. Just factorize it. If you factorize it, you can write it in this term. So that is the multiplication of two terms. One term is R plus j omega L, second term is G plus j omega C. Now let us say R plus j omega L is Z. So Z is equal to R plus j omega L. That will be series impedance per unit length. Why per unit length? Because we are using R and L, not R delta Z. R delta Z, L delta Z would be complete impedance. But R and L are impedances or resistance and inductance per unit length. Therefore, Z is equal to R plus J omega L is series impedance per unit length. Similarly, Y is equal to G plus J omega C, that is parallel admittance per unit length. Using this Z and Y, the equation now becomes d square V by dz square is equal to Zy into V. So that is the equation. We can write the equation in that form. Now, let us define gamma square is equal to Z into Y. So if we write gamma square is equal to Z into Y, the equation becomes, the differential equation now becomes d square V by dz square is equal to gamma square Vz. This is a simple differential equation, second order differential equation, and you can solve it easily. The solution will be of the form Vz is equal to A exponential minus gamma z plus B exponential plus gamma z. Minus gamma z is a direction which is, gamma is here called the propagation constant. Now minus gamma z gives you the propagation in the positive z direction, plus gamma z gives you the propagation in the negative z direction. So Vz will be the signal voltage which is propagating in the positive z direction, will have the form A exponential minus gamma z, and the voltage which is propagating in the negative z direction will be B into exponential plus gamma z. Total voltage will be the voltage propagating in the positive direction plus the voltage propagating in the negative direction. So Vz is equal to this. Now you know what is gamma. Gamma is equal to square root of R plus j omega L into G plus j omega C, because R plus j omega L is Z, G plus j omega C is Y. Okay. Now what will be the correct sign of the square root? That is the question that you have to answer. Okay. Now what we'll do here is we'll take the principal square root, which is the positive sign for the square. So gamma is equal to this. Now, for principal square root, let us say z is a complex number. So z will be in the form r into exponential j theta. Z is any complex number. If it is a complex number in terms of exponential function, you can always write z, any complex number small z, that is called to r exponential j theta. If that happens, then square root of z is equal to square root of r into square root of exponential j theta. Square root of exponential j theta is exponential j theta by 2. So square root of z is equal to square root of r into exponential j theta by 2. Now what will the value of theta here? Theta will be between minus pi to plus pi. That will be the range of the theta. Minus pi is less than theta is less than equal to pi. Now the square root symbol, look at the square root symbol here. You can see that real part of the square root of z is always greater than equal to 0. This equation, this square root z is equal to square root r exponential j theta by 2 with this condition theta between minus pi to pi, that shows that the real part of the square root z is always greater than 0, because r is a real number. Its square root you are considering the principal square root, therefore square root of r is positive. Then exponential j theta by 2 in the limit for theta minus within minus pi to pi, exponential j theta by 2 is always positive. Therefore this will be a real part of the square root of z is always greater than 0. This will not consider gamma. So real gamma will be greater than equal to 0, because gamma is a complex number. Square root of gamma, gamma is a complex number, and it is square root of another complex number. Therefore gamma will be, real part of gamma will be greater than equal to 0. Or how you can say we are considering the principal square root for gamma. Okay. Now gamma is this. We know gamma is equal to square root of r plus j omega l into g plus j omega c, since that is what is gamma. Let us say gamma as a complex number, let us define it as gamma is equal to alpha plus j beta. Gamma is the propagation constant, alpha let us call it a attenuation constant, and beta let us call it phase constant. So propagation constant, it will be per meter, unit will be per meter. Attenuation constant, unit will be nipers per meter, and phase constant, unit will be radians per meter. Now alpha is the real part of gamma. So alpha is always greater than equal to 0. Why it is called attenuation constant, that will be clear later. As you know, we decided V. What is V? V is equal to A into exponential minus gamma z. Now, if for gamma we will put alpha plus j beta, so that will become exponential minus alpha z into exponential uh, minus j beta z. So if I put alpha plus j beta there, so it will become minus alpha z exponential minus j beta z. Minus j beta z corresponds to propagation, and it is related to phase. That is why it is called phase, beta is called phase constant. Now exponential minus alpha z, you know, exponential minus alpha z is a exponentially decreasing function. So the value of V will decrease exponentially because of exponential minus gamma minus alpha z, and that is why it is decreasing, means it is attenuating. That is why it is called attenuation constant. Okay, now we'll consider that uh, the two cases. In one case, we have gamma is a square root of two complex numbers. So the first complex number is r plus j omega l. Since we are considering r plus j omega l, r is positive, omega is positive, l is positive. Therefore, in the complex plane, r plus j omega l, that will be in the first quadrant. So in the complex plane, it will be in the first quadrant. Similarly, G is positive, omega is positive, C is positive. Therefore, in the complex plane, G plus j omega C, that also will be in the first quadrant. So there are two possible locations for the complex square root. So for each one, r plus j omega l and G plus j omega C, the only possibility is they will be in the first quadrant. But for the square root, when gamma, we are considering gamma, now their product will be taken and the square root of that product will be taken. So where will it be? There are two possible states. One is in the first quadrant, because both are positive, their square root will be positive. So that will be in the first quadrant. Then the other possibility is in the third quadrant, because if both of them will be negative, then that indicates that both of them will be negative. So then also their square root will be positive. So the other possibility is third quadrant. So there are two possible locations for the complex square root. The principal square root must be in the first quadrant. So therefore we are considering that. So alpha is equal to real part of gamma, beta is equal to imaginary part of gamma. Since alpha is real part of gamma, beta is imaginary part of gamma, because gamma is equal to alpha plus j beta. So from that, you know, alpha is real part of gamma, beta is imaginary part of gamma. Therefore, considering that it is gamma is in the first quadrant, alpha is greater than equal to 0, beta is also greater than equal to 0. Okay. Now let us consider the wave which is propagating in the plus z direction. B, the only the part that is propagating in the plus z direction. Then we will consider the part that is propagating in the minus z direction. In the plus z direction, V is equal to A exponential minus gamma z, that is A exponential minus alpha z into exponential minus j beta z. as gamma is equal to alpha plus j beta, exponential minus alpha z, that represents the attenuation in the wave as it propagates along the positive direction. Similarly, for the negative direction, exponential plus alpha z, that gives you the attenuation of the wave as it propagates in the negative z direction. Okay. Okay. And now we'll consider the attenuation now. So attenuation in decibels per meter. Now attenuation in decibels per meter, that you can define. How do you define decibel? Decibel is log 10, it is 10 into log 10 of P by P1 by P2 or P out by P in. P is the power. Bell is from power, that you know. Now for power, if you express power in terms of voltage, it is V square by R by L. So P is equal to V square by R. Now we will consider here input and output voltage. So V out square by R by V in square by R. R will cancel out in the numerator and denominator. So V out square by V in square. So V out by V in whole square. V out by V in whole square, log of that is equal to 2 into log of that. So that will be minus 10 into log 10 of V out by V in whole square. Now V out by V in whole square is equal to log of V out by V in whole square is equal to 2 log of V out by V in. So that 2 multiplied by 10, that gives you 20. So attenuation in dB is equal to minus 20 log 10 V out by V in. Now on that you can write V out as A exponential minus alpha z. V in is A. So when z is equal to 0, that gives you V in. So V in is A. So from that you will write minus 20 log 10 into A exponential minus alpha z by A. A cancels out. Now log 10 exponential minus alpha z, that you can write as minus 20 into 0.4343 into minus alpha z. As you know, log 10x is equal to 0.4343 into log natural x. Therefore, attenuation in dB per meter is equal to 8.686 into alpha. Now we will come to wave number notation. Now look at this. V is equal to A exponential minus gamma z, that you can write as A exponential minus alpha z exponential minus j beta z, and that if we write as A into exponential minus j k z z, instead of writing exponential minus gamma z, we write it as exponential minus j k z z, where kz is equal to, so now gamma is equal to jkz. If you write gamma is equal to jkz, so from that you can say kz is equal to beta minus j alpha. So in that form, if we write kz is equal to beta minus j alpha, then we'll write kz, we'll call the propagation wave number, and we can write kz from gamma. Gamma is equal to kz, jkz. From that we can find out what is kz. Kz is equal to minus j root over of r plus j omega l plus a into g plus j omega c. So in terms of propagation constant, we have defined what is called a propagation wave number. Okay. So and now let us consider again the forward traveling wave. A wave traveling in the positive z direction, that you can write as positive. For positive you can write V plus. So V plus Z is equal to V0 Z. V0 is the voltage when Z is equal to 0. So V0 plus exponential minus gamma Z, that you can write in terms of alpha and beta. So if you do that and express everything, then and take into consideration the time variation. Time variation is of the form exponential j omega t. So multiply that exponential j omega t, then small v plus. Now what is the difference between small v plus and capital V plus? Capital V plus contains only, consists only the spatial variation, the variation in space. Small v plus consists of the spatial variation as well as temporal variation, variation in space and variation in time. Therefore, small v plus is a function of z and t, whereas capital V plus is a function of z only. So, a small v plus will be capital V plus into exponential j omega t, real part of that. So, if you take the real part of that, that you can find as b0 plus exponential minus alpha z into cos omega t minus beta z. So, and this indicates that the wave will repeat itself when beta into lambda z is equal to 2 pi. Lambda g is the wavelength, wavelength within a guided wavelength or the wavelength on the transmission line, that is lambda g. So, when beta into lambda g is equal to 2 pi, this will always repeat itself, the wave will repeat itself. Okay, where beta, what is beta? Beta is equal to beta into lambda g is equal to 2 pi. Therefore, beta is equal to 2 pi by lambda g. Right. So that equation is that if you express that equation in terms of a graph, in terms of a, yes, in terms of a plot, the plot will be like this. The snapshot of the wave is shown below, where you have lambda g, you have t at t is equal to 0, what is the snapshot. Then at t is equal to 1, t is equal to 2, that you can find out. So here we will take a break. We have considered enough thing to take a break here. Then we'll come back and consider other parts. Let us stop here. Let us take a break of 5 minutes. After 5 minutes, I'll come back. So you can relax for 5 minutes. Then we'll start.